Now, let us start section 2, special lines and planes attached to surfaces and space curves. First, let us go through an introduction. Let us gather some tools that are required to deal with the problems pertaining to this topic. So, in the introduction, we will first go through the normal vector to a surface. Let us come up with this operator first. This operator is defined in 3D. This is called the gradient operator or sometimes grad operator. Here you have partial derivative of partial derivative of x, that partial term attached with attached with the unit vector along the positive direction of x axis, which is I. Similarly, partial over partial y is attached to j, partial over partial z is attached with k. Now, let us consider this surface, this function x squared plus y squared plus z squared minus 1. Now, if you find grad phi, this is a grad operator, this is phi. Now, this phi falls into these traps. So, you will end up with this one, right. Here this one falls onto this one, you will get this is the second term and this is the third term. Now, when you partially differentiate this term, this function, you get 2x. Here in the second term you get 2y, here you get 2z. Now, you get a vector. So, grad phi is a vector. Now, we will see what it is and how we can interpret this one. So, if you take this point 1 0 0, that is on the x axis, the value of x is 1, it is this vector, it is this point. Now, if you evaluate this grad phi at 1 0 0, you get 2, here you get 0 0, so you get 2I. So, it is in the direction of it is in the positive direction of x axis. Similarly, at 0 1 0, where the x coordinate is 0, y coordinate is 1, z coordinate is 0, it is this point. It should be on y axis because both x and z coordinates are 0. And again, if you plug in these values, you get 2j, grad phi is 2j. So, again it is in this direction, in the positive direction of y. Similarly, at 1 1 1, you get 2I plus 2j plus 2k. So, it is like this. Again, the vector is directed from the origin, right, but it is pointing towards this direction. Similarly, at minus 1 0 0, you get this vector minus 2y. It is in the negative direction of x axis. So, how can you relate this to this function phi? Now, let us sketch phi is equal to 0. Now, this is phi. When this is equal to 0, you get x squared plus y squared plus z squared is equal to 1. So, you get this sphere, the unit sphere centered at the origin. Now, again if you mark these vectors, for example, this one you have it here, again this one you have it here, the vector at minus 1 0 0 is at this point. So, you can see that if you move in in these directions, the function we had, which is phi, this function, right, this function increases because look, forget about minus 1 is a constant. So, this function basically depends on x squared plus y squared plus z squared. So, that is the square of the distance from the origin. If you just ignore this minus 1, x squared plus y squared plus z squared means the square of the distance from the origin to that point. So, if you move in this direction, what happens? The distance increases. That means grad phi is directed in the way that the function, the value of the function increases, right, the function phi. In this case, what happens is that x squared plus y squared plus z squared increases if you apply grad phi. So, it is simply the square of the radius. So, if you think about this is like a balloon, if you increase the radius, if you increase the value of the radius, you have to increase the volume of this one. So, every point like this point moves away from the origin, every point on the surface moves away from the origin, right. That means that vector is always perpendicular to the surface. Like here you can see that it is perpendicular in this case, like just to increase this, say there is a point on the balloon. So, if you increase its volume, that point moves away from the origin. So, that direction is always perpendicular to the surface, right. Therefore, in fact, for any surface phi, so let phi be equal to 0, then grad phi is always the normal vector to that surface. This is just a special case, but in general it is true for any surface phi, right. I just wanted to demonstrate what it is using this sphere, right. So, once you have it, you can also always see that the normal direction or the normal vector is not unique, but normal direction is unique. Think about this, take this board, take this point. Now, there is only one normal, right, to the surface, but if you take this line, there are infinite normals. Look, this is a normal. If I draw something like this, this is again a normal to the line, this is a normal. Therefore, there are infinite normals to a line, but to a plane there is only one normal direction, right. That unique normal direction can be obtained using grad phi, right, for any surface. Now, let us move to the tangent vector to a space curve. Now, we know that a space curve is always given as the position vector when a parameter, let that parameter be t, when t varies through real values. Now, say for some particular value of t, the position vector is this one, let that point be p. So, the parametric value is t. Now, if you give an infinitesimal change to that t, it will increase to t plus delta t. Now, at that point you have you are in a different point, but which is nearby, right. Therefore, p and q sit nearby, but they are different because of this delta t. Now, you can find the vector p q. Now, at t plus delta t, this is the position vector, at t this is the position vector. Therefore, this difference can be obtained like this vector minus this vector. So, p q is r evaluated at t plus delta t minus the vector at this point r t. So, you can find p q. When you divide it by delta t, when you divide this vector, I have forgotten the vector sign. If we divide that vector by delta t, still it is a vector in this direction, in the direction of p q, right. There what happens is this, you have p q, now you have vector like this. Now, that is a kind of a code. Now, to make it a tangent, you have to bring this q along this curve. To do that, you have to decrease this delta t in value. So, to do that, you let delta t goes to 0. If you do that, p and q almost coincide, they come like close to each other. At that point, you will get the tangent drawn at p. So, the tangent vector to r t at p is this one. Now, this is the vector p q, you divide it by delta t, still it is a vector along p q direction. Now, if you take this limit, you know that by definition of the derivative, this is dr by dt, the derivative of r with respect to t. So, that gives you the tangent vector at p. Early it was like this, once q comes towards p, and finally it will be like this. it will be it is a tangent to the space curve at point P. So, by dr by dt you get the tangent vector at point P. That is also unique. The tangent vector to a space curve is unique. There is only one of them, but there are infinite normals you can draw at point P. This is a normal, this is a normal, and this is another normal. However, there is only one tangent vector, I mean one direction. Now, before getting into problems, we need to have this relationship. It will make our life easier. It will be very useful it will be handy once we have that at our disposal. Now, take this vector. P is a known point. X is capital X is any arbitrary point with coordinates x, y, and z. Now, the vector Px is can be given like this. It is a simple thing. I do not want to explain that. Now, let a vector V is a constant vector having these components. So, you have it as ai plus bj plus ck. Now, there are two special cases. If you have first case, when Px is parallel to V, when Px is parallel to V, you can write Px is equal to kV, where k is a scalar. Then by equating the components, you can show that their respective components have the same ratio, like x minus x naught over A, y minus y naught over B, z minus z naught over C are all equal. It is like this. For example, if Px is 2y plus 2j plus 4k, 2 to 4 is parallel to I plus j plus k, sorry, I plus j plus 2k. Here 2 to 4, here 1 1 2, like that. They should maintain the same ratios. When Px, the vector Px is normal or perpendicular to V, you can always take their dot product is equal to 0. Now, if you take the dot product, this is vector Px, this is vector V, you know how it goes. I dot I is 1, therefore, A goes hand in hand with this one, B goes hand in hand with y minus y naught, C goes hand in hand with this one. So, this is what you get. In fact, in this case you get a plane, equation of a plane. Here you get the equation of a line, right. And always when you find normal planes, tangent lines and stuff like that, you always need this format. Either you get it like this, once you have this vector V. Vector V is that you need unique direction, like pertaining to a space curve, that vector V is this one, tangent vector. Pertaining to a surface, that vector V is what? This unique direction, which is the normal vector. Once you have that, you decide what you need to find, and accordingly either you will find it in this way or this way, right. Okay. Now, after this we will take up some examples, right. Okay. Thank you.